Right, good morning, ladies. Let's recap. So, at this stage, you all know that Boyle's law is all about the relationship between pressure and volume, and you know that pressure and volume are inversely proportional at constant temperature. The next gas law that we need to look at is Charles's law, and this law describes the relationship between volume and temperature at a constant pressure. And this is what the law looks like. So if you get a question to state Charles's law in words, this is what you would write down. The volume of an enclosed gas is directly proportional to its Kelvin temperature, provided the pressure is kept constant. So according to Charles's law, volume and temperature are directly proportional, but very important, it has to be the temperature in Kelvin, which we have spoken about already, but I'll remind you about that shortly. So, in your textbook, on page 145, there's activity 7.2, which you can try if you feel like it. It is quite simple. So they say that you should use a bottle with narrow neck, something like this, and then fit a balloon over the neck of the bottle, and that's what they've done over there. And then you take the bottle and you place it in a container with hot water, maybe in a pot with boiling water, and then you'll see that the balloon will slowly start inflating slightly. And this illustrates Charles's law, because the gas inside the bottle is heating up, so increase in temperature. So what happens, there's an increase in volume, and that is why the balloon starts to inflate. So this shows the direct proportion between volume and temperature. Now, also on page 145 of your textbook, there's experiment 7.2, and the whole experiment, you can go read through that as well. They talk about using a gas syringe with a plunger. So you take the gas syringe, fill it up with air, and then place it in a beaker with ice. So what should then happen is, because I'm decreasing the temperature, the volume should decrease, and the plunger of the gas syringe should actually start moving inward so that there's a smaller volume. If I take that same gas syringe and I place it in boiling water, so I increase the temperature, the volume is going to increase of the gas inside the gas syringe, and the plunger will actually start moving outwards. But as I said, you can read that yourself, and this is what you need to look at. This is a typical set of results that you would get from an experiment like that. So here you are interested in temperature readings and volume readings. So as you can see over here, the temperature in degrees Celsius is 10, the volume is 50 centimeters cubed. If the temperature is 30, the volume is 53,5, and so on. So from these results, we can see that temperature and volume are directly proportional. As temperature increases, volume increases. But because we've already said, when we're busy with gases, what must temperature be in? It must be in Kelvin. I've got another column over here where I've got the Kelvin temperatures. And here's your reminder over here. If I've got temperature in degrees Celsius, to work out the Kelvin temperature, I just need to add 273. So 10 plus 273 is 283. 30 plus 273 is 303. So that's how I got these Kelvin temperatures over here. And then in the last column, I've got volume divided by temperature in Kelvin. So if I take 50 divided by 283, I get 0,18. If I take 53,5 divided by 303, I get 0,18, and so on. So I can see that volume divided by temperature in Kelvin gives me a constant answer for this specific set of results. Then they ask some questions. They say, what do we see about the value of V divided by T? And as we've already said, it's a constant value. And then they ask you about the different graphs. So they ask you about the shape of the graph and so on. So the first one is where I have got volume on my y-axis and I've got Kelvin temperature on my x-axis, as you can see over there. So what I've done is I've plotted those points according to my previous information in the table. So I've used this information over here. And when I draw the line, it ends up looking something like this. So to simplify, I can clearly see that volume and temperature in Kelvin are directly proportional. So if I had to describe the shape, I would say that it's a straight line to the origin, and clearly what does it show? It shows that direct proportion between volume and temperature in Kelvin. But then if I go and I draw another graph of the temperature in degrees Celsius and the volume, it ends up looking something like this. So now just ignore this bit here for now and just take a look at what's happening over here. So on my y-axis, I've got volume again. On my x-axis, I've got temperature in degrees Celsius. So if I plot those points, it ends up looking like that. If I then go and I extend my x-axis so that I've got negative temperature values as well. So I've got negative 50, negative 100, and so on. And I extend this line, as you can see over there. It intercepts the x-axis over here just before negative 300, and that value there is actually negative 273,15 degrees Celsius. So that, if I round that off, that is where the 273 comes from for converting degrees Celsius to Kelvin. So this also then shows me that negative 273 degrees Celsius is the equivalent of 0 Kelvin. So I'm just going to say this again. If you plot a graph of just volume versus temperature in degrees Celsius, it still shows direct proportion, but it looks like that. If I extend my x-axis and I extend this line over here, where is it going to intercept my x-axis at negative 273,15 degrees Celsius? Okay, right. And then, of course, the formula that we use for Charles's law looks like this. V1 divided by T1 is equal to V2 divided by T2. And the most important thing in this formula is that both temperatures must be in Kelvin. So just to quickly show you, where do we get that from? If that is my V1 and that is my T1, V1 divided by T1 is 0,18. If this is V2 and T2, V2 divided by T2 is 0,18, and 0,18 is equal to 0,18. So V1 divided by T1 is equal to V2 divided by T2. So that is the formula that we see over there. And let's take a look at an example of a question. So 20 centimeters cubed of a gas at 15 degrees Celsius is heated. So there's my volume 1 and that's my temperature 1 that goes with it. Until the gas reaches a volume of 47 cubic centimeters while being kept at a constant pressure, what is the temperature of the gas in degrees Celsius? So V2 is 47 and T2 is what I want to work out. They ask for the temperature in degrees Celsius. It doesn't mean that they give us permission to use degrees Celsius in the formula. The formula temperatures must be Kelvin. So that just means I've got an extra step where I go convert the Kelvin back to temperature. So take a look at what I've done here. So volume 1 is given as 20 cubic centimeters. Volume 2 is 47 cubic centimeters. Again, the two volumes must have the same unit. So if those units are different, convert them so that they're the same. It doesn't matter which one. So centimeters, centimeters cubed, so that's all good. The temperature one is given as 15 degrees Celsius. It must be in Kelvin. So 15 plus 273 gives me 288 Kelvin. I write down my formula. V1 divided by T1 is equal to V2 divided by T2. Substitute my values. Do the maths. Get T2 alone on one side. I get the answer. And what is the answer going to be in? The answer is going to be in Kelvin. That just means that I must have do that extra little step where I take the Kelvin temperature, I minus 273 so that I've got the temperature in degrees Celsius, because that is what they asked for. And then another example here. A certain amount of gas is heated until its volume is doubled while being kept at a constant pressure. So I don't know what the volume is. I just know that it's doubled. So I've done it like this. I've said, okay, V1 and V2. So one must just be V and the other one must be 2V. Or if you want to use X, the one must be X and the one must be 2X. Then they say, once the volume has doubled, the gas is at a temperature of 353. So the 353 goes with the 2V or the 2X. But once again, it must be in Kelvin. So I add 273, which gives me 626 Kelvin. Then they say, what was the original temperature? So I want the temperature when the volume was V. So it's this temperature that I want to work out. So in actual fact, even if these are your ones and these are your twos, it doesn't matter, just as long as your V goes with the temperature you want to work out and the 2V goes with 626. So formula written down, values filled in. I've done the maths. I got T2 alone on one side. The V's will cancel out. 626 divided by 2 gives me a temperature of 313 Kelvin. But the question specified I want temperature in degrees Celsius, so minus 273, and that gave me an answer of 40 degrees Celsius. So what you can do now, I've got two questions, well actually three questions, because we've got two questions there that you can go do to practice Charles's law. Thank you, ladies.